To do the classic retirement problem. There are about, I don't know, 2 different ways that we can do this problem in terms of like setting it up. So if I'm a professor, it's almost always the same. Somebody starts saving when they're 25 or 35 or 40 or whatever. They save a certain amount. They may take a break or they may retire directly after that. So how much are they going to have when they retire? What I'm going to show you today is that it doesn't matter if you calculate the future value or if you calculate the present value and then push it forward to when she retires. It makes sense either way. Okay, so first of all, I'm going to set up 2 timelines here. So Jessica just turned 25 and time is 0. So we are standing in today where time is 0 and she just turned 25. And oops, cash flow. She is going to put $10,000 into her account. And she is going to do that every year for 10 years. I'm sorry, 25 years. Okay, so let's and if she does it 25 times, that means in year 24 that she'll stop contributing. And like if I did this on a problem, so I just made up this problem, I would make it clear that she only made 25 contributions, just so like everybody worked the problem correctly. But this is the setup that I had in mind, even if I didn't word it well. Okay, so from then on out, I am going to start not making a payment. And she is going to do that for 15 years. So 1, 2, 3, 4, 5. Let's just make this easier. And so therefore we need 1 more year. All right, so she doesn't contribute for the next 15 years, at which point she retires. So that's going to be 0. And oops. Okay, so here we want to solve for this number. We want to figure out how much she's going to have when she retires. Now there's a lot of different ways to do this, so let's do the present value method. What's the interest rate? I didn't even talk about the interest rate. Let's say the interest rate is 6%. Okay, so R is going to be 6%. Present value is just going to be $10,000 divided by 1 plus R. I'll lock the cell to the power of t. Notice the power of t is 0 here. That means that this is just going to evaluate to $10,000. So I'm going to drag this all the way down. The rest of these are going to be 0 because there's no cash flow, so I can be lazy and not do the formula. And now let's do the net present value, which is just going to be the sum of all these. Okay, now this is the amount that if I were standing in time 0 at age 25, that I could just put into an account and it would grow into the future. So like this is the present value in time 0, but now I need the future value. And so what I'm going to have to do is inflate it or compound it. So 1 plus R to the power of the number of time periods, and this is 39 time periods because that is how many time periods we need. And so we end up with $1.314 million. Okay, now let's see if we can use the future value method where we push these cash flows forward and get the same answer. So I'm going to hide this for a second. Hide. Okay, so we are going to multiply it because we're going forward, and we are going to raise it to the power of 39 minus 0. And what I'm going to do is make sure I get these parentheses right. So instinctually, like contextually, here's what we're doing. We are going to raise it to the number of time periods that exist between this and this. So let's see if this works. Again, we have no time periods here, like after that, so we don't have to do it for these. Okay, so now let's take the sum. And let's highlight this, put a comma in it, make it all pretty. And now let's compare these. Move over, Jessica. There we are. And we have the same number. So let's talk about what happened just to wrap this video up. I created the future. So in this part, I took the present value. So I discounted all these back to today's value. So if Jessica's 25, her account, you could offer her to either save $10,000 a year for 25 years, or you could allow her to have a check for $135,000, and if you put that in the bank, it would grow to $1.3 million. The future value says, okay, if I put this $10,000 in the bank, in 39 years, it'll grow to $97,000. This one will grow to 91, and so we just sum up all those cash flows in the way that they grow in the future, and we get 3.14. So this is the quintessential retirement. It's not really a problem, but like everybody does these in these classes, and I've showed you that you can do it both as a present value by discounting it back to the current day and then inflating it to the future, or you can inflate the cash flows to the future and get the same answer.